Hello, in this video, I am going to discuss Cambridge International A-Level Physics, Paper 5, May, June 2024, Paper 52. Now, let us begin with the first question first. The first question, a spring is attached to a strong cylindrical magnet of length L and cross-sectional area A. The magnet is placed on a thin cord on top of a magnetic sheet on the bench as shown in Fig 1.1. So you have to remember this is a thin cord, right? And the thickness of the cord is T. Magnetic flux density at one of the poles of the magnet is B. A force is applied upwards to the spring, pulling it upwards. Extension of the spring where the magnet just leaves the card is S. It is suggested that S is related to T by the relationship Ks equals ALBZ over T, where K is the spring constant of the spring and Z is a constant. Plan a laboratory experiment to test the relationship between S and T and draw a diagram showing the arrangement of your equipment. Explain how the results could be used to determine a value for Z. In your plan, you should include the procedure to be followed, the measurements to be taken, the control variables, more than one, the analysis of the data, and any safety precaution to be taken. Now, let us begin with this question. When I see a question like this, right, to help me to get an idea, I will actually look at the one that we are asked to investigate. So we are asked to investigate the relationship between S and T. So S and T, one will be your independent variable, the other one will be your dependent variable. And based on this relationship, other than S and T, those are all variables to be kept constant. That you can talk about how you keep all those variables to be constant in the final part of this question, which is called additional details that will give you a lot of mark plus safety precaution. Right, now let us begin with the diagram. Since I have already planned, okay, I have to come up with the relationship, which one I want it to be the independent variable and which one I want it to be the dependent variable. So I am going to put T as the independent variable because it is easier for me to alter, right? It is easier for me to change, right? Vary. So the other one will be dependent variable, which is S. And variables to be kept constant, what is left in the equation suggested here, those will be your variables to be kept constant. So you can state more than one. You need to state more than one because the variables means plural. So I put K, spring constant. I don't have to explain the symbol because all the symbols have already been explained in the question. So you can save your time in writing it back, right? So A, L, B. As long as you write more than two, write more than one, sorry. As long as you write more than one, you're safe. Now, after that, I would like to begin with the methods of how the experiment is being conducted. So remember, we are just a planner. I am just a planner. I'm not the one that conduct the experiment. Before I come up with the method, I need to have a diagram to refer to. Each and every time, even the question mentioned, you may not draw a diagram, but I would strongly suggest you to draw because by drawing the diagram, you can see the overall, what is happening, what will happen because you are the planner, remember? What will happen during the experiment so you can plan your experiment in a nicer way instead of you cancel here and put arrow up there, arrow down here. That would be very, very messy. Don't you think so? Now, this is my setup for the experiment. This is my diagram. I have a Newton meter. Do you still remember what is the function of Newton meter? Is used to measure the force. Remember, the force is being applied upwards, and my spring a little bit long. Don't you think so? Okay, just forgive me for that. And then the other end of the spring is attached to the magnet, cylindrical magnet, and the upper end is attached to a Newton meter to measure the force that is being applied to the spring. And I have a G clamp in in just to make sure that the magnet sheet is not being pulled out by the cylindrical magnet. So that is why I have to clamp it there so that it won't follow the cylindrical magnet when the magnet leave the sheet. And I have a meter rule because I need to measure the extension of the spring. I have a retort stand because meter rule cannot stand by itself. And to make sure that meter rule is vertical, I use set square 1. The function of a set square is used to make sure that the meter rule is vertical. And I use a set square too because there's a little bit distance between my spring and my meter rule. So I need a pointer. I need a guide, yeah, to show me what is the reading on meter rule because I cannot look at the air, right? So to make sure that the experiment is more accurate, I use another set square, which is set square 2, as a guide to the reading on the meter rule. So let us begin with our procedure here, method. So I say the first method is, of course, set up the apparatus as shown in diagram. That's the first part. And the second part, I say that I measure the initial length of the spring first before the spring is being attached to the magnet. Initial length of spring. Please suggest the apparatus. Initial length of the spring is measured by meter rule. I use a meter rule to measure the initial length of the spring. And then after that, third, I said that the T, wow, this is my independent variable. So I got to talk about T. T is measured by micrometer screw gauge. Remember, it has to be thin, right? And okay, T is started at, I suggest a reading for T because I need to make sure that it is thin enough, 1.5 mm. And then after that, a force, I suggest a force as well, 10 Newton is applied on a spring. Force is measured because the examiner will surely wonder, how do I measure that 10 Newton? So I say the force is measured by Newton meter, or you can call it as Newton spring balance, not a problem, right? And that's it for part 4. And then part 5, once the force is being applied, of course, the spring will extend, right? Now I need to measure the final length. Final length of spring is measured by meter rule again. And then after that, S, I just need to tell, how do I calculate S? S is not being measured, it's the extension. S is calculated by final length of spring minus initial length of spring. I'm done. And of course, you just leave it like that because you need to repeat the experiment. Remember, experiment is repeated with T equals to maybe 2 mm, maybe 3 mm, 1, 2, 3, 4 mm, 1, 2, 3, 4, 5 reading, 5 mm, and 6 mm. So 1, 2, 3, 4, 5, 6. At least you need to have 6 sets of readings, right? So I'm done with my method. So after the method, we need to analyze the data. So analysis. Remember to write 3 points for your analysis. And analysis is the easiest part to score full marks. So first one, you just need to tell what type of graph that you want to plot. I'm supposed to plot graph of S against 1 over T is plotted. So I actually modified the equation. So I get, should remember this one. I will move on to this. I put S as a subject, so I have S equal to ALBZ over K times 1 over T. Could you see that? And you compare with the straight line graph. This is y-axis, this is your x-axis. You have only gradient. You do not have the y-intercept, right? So that is why the second point will go to, okay, if a straight line graph passing through, so you have to be more specific, passing through origin is obtained, then the relationship is valid. That's all. And the third one, remember the question asks you to find here. Explain how you use your result to determine the value of z. Of course, you need to determine from the graph. Now, I just write down my gradient is actually equals to ALBZ over K. Now, to determine the value of z, make z as the subject. It is K over ALB times the gradient. That is how you determine the value of z from the graph. And we are done with analysis. Now we move on to details and safety precautions. Remember, this part will give you 6 marks. So you need to write at least 6 points. So I'm going to write the first one. I said that because remember, for details and safety precautions, if you have lack of idea, you don't know what are you supposed to write, right? I strongly suggest you to refer to your variables to be kept constant. They are variables. But during this experiment, you want to keep all these variables to be constant. How do you do it? Discuss at that part. So firstly, I would talk about the A first. The surface area of the spring. Remember, A is the surface area, cross-sectional area of the spring. How do I keep it constant? How do I calculate it? Right? Now, because I need the value of A, I need the value of surface area of cross-sectional area of the spring in order for me to calculate the value of Z here. So you need all this value. You need A, you need length, you need B, right? To calculate, and you need K, spring constant. Talk about that in details and safety precaution. Now, first of all, I say that diameter of spring is measured by micrometer, screw gauge. A can be calculated by equation. A is equal to pi d squared over 4. Do you know how do I get it? So now I want you to look at my spring. My spring is a circular shape. So that is why it is the surface area of the circle. So the surface area of the circle, I know, yes, I will write it here. A is equal to pi r squared. But you have to bear in mind there's no apparatus that we could use in the lab that could be used to measure the radius of the spring, right? So I need to use the micrometer screw gauge to measure the whole diameter of the spring. So, but there's a relationship between the radius, this is called radius, and this is called diameter. Yeah, 2 times radius is diameter. So that is why radius is equal to diameter over 2. Sub into the equation, what do you get? Diameter over 2, you square it, you get pi d squared over 4, like the one that I show here. That's it. And the second point, I am focusing on B, magnetic flux density or the magnetic field strength. This is a little bit of headache here, right? I say B is measured by using Hall probe. Okay, I extra bit that place close to magnet because I want my reading to be maximum. But what if the reading, how do you know that that's the reading, whether it is the maximum reading? Because B, the Hall probe must be perpendicular to the magnetic field of the magnet. And God know that we can't see something that is invisible. Can't you see the magnetic field? I don't think so because I can see. Okay, we cannot see magnetic field. But how do we know that is the maximum reading? So you need to test an error, test here and there, right? So I talk about that um, to make sure B and Hall probe are perpendicular or right angle to each other. Probe is rotated until a maximum reading is registered on meter. Normally, the Hall probe is being connected to millivoltmeter. It is quite small, the value of the magnetic field. Now, the third part, I want to measure K. I want to calculate K, right? First of all, I take the spring initial length of spring is measured by meter rule, and then a slotted mass of maybe I use 10 gram, yeah, is measured by Newton meter, and attach to spring. Final length of spring is measured by meter rule, extension of spring. I use it at X equals difference between two lengths. Or you can say final length minus initial length, right? So K can be calculated by equation K equals to F over X. Right? A slotted mass of 10 gram. Yeah, the force, right, is measured by Newton meter or Newton spring balance. And that is how I measure. And number 4, I said measurement of extension, which is S, yeah, is repeated along the card and average. And then I said that I use a G clamp. Actually, if I don't want to explain this because I have already stated, I already drew it out in my diagram, but I still want to explain it because I have time. G clamp is used to clamp magnetic sheet to bench. And then I said also that make sure one of the safety precaution is that make sure the one that you can see, no other magnetic materials nearby. And I would like to talk about the set square. Yeah, set square. Oh, I give you more than 6 points. One is used to make sure rule is vertical. Set square 2 is used as a pointer to read from meter rule. And that's it about the first question. I hope you can understand the first question better. Now, let us dive into second question. Number 2, a student investigates the resonant frequency of a metal rod. Metal rod of length L is suspended from 2 rubber loops. A sensitive microphone with a cone is positioned at one end of the rod. A microphone is attached to an oscilloscope as shown in Fig 2.1. The rod is hit gently with a hammer, and the period T of the trace produced on the oscilloscope is determined. The experiment is repeated for different values of L, and it is suggested that T and L are related by this equation. T is equal to 2L to the power of n divided by C, where C and n are constants. Now, a graph is plotted of log t on the y-axis against log L on the x-axis. Determine expressions for the gradient and the y-intercept. Now, since they already told us that they want us to plot the log graph, so you have to log both sides. Now, I log t is equal to log whole thing 2L to the power of n divided by C. Log t is not a problem. Now, log, right? Log, this is log 2 plus n log L, because this is divide, so you minus log C. This is a little bit of math here. And they said that log L. Okay, so I put log T is equal to n log L first plus log 2 minus log C. Now I compare with the straight line graph equation. Y is equal to mx plus the whole thing here give you y-intercept C. The gradient of the graph would be n. The y-intercept will be log 2 minus log C, or you can simplify it to become log 2 divided by C. Not a problem. The next one, values of L and T are given in table 2.1. Calculate and record the values of log L and log T in table 2.1. Include the absolute uncertainty in log T. So I will put log T aside first. I will calculate log L first. So log L is being calculated from L values. So since the calculated value, I'm still using the AS method. Calculated value must follow the significant figures of its raw data. Raw data is the data that you use to calculate. Since L, the first L value has 2 significant figures, so my log L, I would just put 2 significant figures, which is 1.7. The next one, L has L, which is 70 cm, 2 significant figures. That is why log L would take 2 significant figures as well, which is 1.8. Third, L is 86, which is 2 significant figures. Therefore, log L would take 2 significant figures, which is 1.9. Third, 1, 2, 3, 4, 4. L is 108, which is 3 significant figures. Therefore, log L must denoted as 3 significant figures, 2.03. And 1, 2, 3, 4, 5. L is 140 cm. Log L, 140 is 3 significant figures. That is why log L would take 3 significant figure, 2.15. And the last reading, L, 167, which is 3 significant figures. Therefore, log L would take 3 significant figures, which is 2.22. Now, look at the question. They ask us to include the absolute uncertainty in log T. First thing I do, I would like to put plus minus sign in between first. Before I calculate the value of log T, I will calculate delta log T first. Do you know why? Because I'm still following the AS syllabus. First, absolute uncertainty must be denoted in one significant figure. And since the reading is included with its absolute uncertainty, therefore, the reading will have to follow the decimal point of its absolute uncertainty. That's the reason why I calculate the absolute uncertainty first. First reading. Now, log T. Oh, this is T value. So if you want things to be easier, you just use log larger, right, which is 25. Log 25 minus log average value. 24 is actually the average value between 25 and between 23 and 25. So some of the books you might see that they will tell you to use log 25 minus log 23 and then divided by 2. So save the troubles, right? Save your time. So you just use the log larger number minus the log smaller number. So log 25 minus log 24, I got 0.02. I would like to put it in terms of one significant figure. The second one, log 33 minus log 32, I got 0.01. Third, log 40 minus log 39, I got 0.01. Log 50, this is 49 plus minus 2. So it is log 49 plus 2, which is log 51. So you get to take log 51 minus log 49. Be careful with the absolute uncertainty given here. So it is 0.02 I got here. Now, okay, and the fifth reading, it is log 66 minus log 64 because plus 2, which you will get 0.01. And the last, log 76 minus log 74, which you get 0.01. Now, since I got all my absolute uncertainty, it is very easy for me to fill in my log t value. Log 24, I put it in terms of 2 decimal points, which is 1.38. Log 32, 2 decimal points as well, 1.51. Log 39, 2 decimal points, I put it as 1.59. Log 49, 2 decimal points, which is 1.69. Log 64, 2 decimal points, 1.81. Log 74, 2 decimal points, 1.87. Done. Now, plot a graph of log t against L, log L. Include error bars for log t. I have pre-plotted the graph. So the graph, straight line graph, you have to make sure that the best fit line passes through most of the points, and that is your best fit line. And then draw best fit line and worst acceptable line. For worst acceptable line, you need to draw your error bars. The absolute uncertainty represents the error bars. So how tall the error bar is. Look at your absolute uncertainty, which is included in log t. Log t is y-axis. That is why your error bar must be vertical error bar. 0.02 represents the height measured from the center of that point. Let us see 1.38. 1.38 is somewhere here, somewhere here. So at the center of the point, the cross that you measure, you need to make sure that 0.01 up and at the center 0.01 down. That is how you draw your error bar like this. Okay, for the second value, it is still the same thing, 0.01, look at 1.51. So 1.51 going up from the center, right? Measure upwards distance or the height, which is 0.01. And then from the center downwards, 0.01 as well. So this, okay, 1.59, 1.69, 1.89, and 1.87. You can do the same, right? Now, plot your worst acceptable line. For the worst acceptable line, there are actually two worst acceptable lines. So it all depends on the first error bar and the last error bar. So if you start from the head, the top of the first error bar, you have to end at the bottom of the last error bar. Or you could also start from the bottom of the first error bar, but you end at the top of the first error bar. So it depends on which worst acceptable line that you wanted to draw, right? Just draw one will do, right? I draw from top to bottom. And after that, okay, determine the gradient of the best fit, include the absolute uncertainty in your answer. So to include the absolute uncertainty in my answer for the gradient, I need to find the gradient of the worst fit as well. So now let me do the gradient of the best fit. I took 2 points here, and you need to show from the graph that how do you calculate your gradient. You need to draw the triangle. So the size of the triangle that you use to calculate the gradient must occupy at least half of the length of the straight line graph that you drew. So the 2 points that I used were, okay, 1.9 minus 1.41, divide 2.22 minus 1.72. And the answer that I got from here is 0.98. What about this? 1.895 minus 1.4, divide 2.6 minus 1.71. Okay, for this one, I got more. So you take more significant figures, 6, 2. Now done with that, to calculate the absolute uncertainty, very easy. You just take the larger value minus the smaller value. Find the difference between the two gradient values and put it in terms of one significant figure as well, because at the end of the time, this is absolute uncertainty. Minus 0.98, and I got 0.4. So just put plus minus first, fill in the value of your absolute uncertainty. The value of the gradient must follow the decimal point. One decimal point, 0. It is actually 1.0. I'm done with that. Now, determine the y-intercept of the line of best fit. Include the absolute uncertainty in your answer. Now, the bad news that I want to share here is that look at your y-axis. It doesn't start from 0. That is why you cannot read from the graph unless your y-axis starts from 0. Right. Now, no choice. We have to use a straight line equation. Remember, y equals to mx plus c. I am going to use that. So I'm going to do that for best fit line first. I put this best fit. The coordinate that I want to use for my best fit, let me see which color represent my best fit is orange color. I am going to use 1.72 and 1.41. 1.72. Okay, I'm going to use 1.72, 1.41. Right, so this one is 1.41 and best fit gradient is 0.98. 1.72 plus best fit y-intercept. So make y-intercept as the subject. I'm going to calculate right now. 0.98 times 1.72, and then you just take 1.41 minus the answer. And I got negative 0.2756. Now for the worst fit, the coordinate that I wanted to use maybe for the worst fit, 2.6 and 1.895. Okay, 2.6. 1.895. Now, using the same approach, y is equal to 1.895. And then, gradient of the worst fit, which is 0.5562. It is okay if you put 5562. It is okay if you put more significant figures because that's not the final answer. So times 2.6 plus worst fit y-intercept. So 0.5562 times 2.6 and then 1.895 minus that. And I got, 0.5562 times 2.6, 1.895 minus that. And I got positive value, which is 0.4489. So the absolute uncertainty of my y-intercept would be 0.4489 minus negative 0.2756. Now I got 0.7. Yeah, 0.7. So I put plus minus 0.7 here. And then fill in for y-intercept, you need to fill in the value of the best y-intercept, 0.3. Now, using your answers to A, C2, and C4, determine the values of N and C. Include the absolute uncertainty in your value. You need not be concerned with unit. Right, now, gotta look at my value of N here. Gradient is N. That is why, okay, N is equal to my gradient. Just put the gradient. Include the absolute uncertainty. So this is 1.0 plus minus 0.4. 1.0 plus minus 0.4, right? So 1.0 plus minus 0.4, they ask us to not be concerned with the units. And then what about y-intercept? Y-intercept is log 2 divided by c. I need to find the value of c. Y-intercept is equal to log 2 divided by C. Y-intercept that I got was, okay, negative 0.2756. I find the best y-intercept first is equal to log 2 over C best because they asked us to include the absolute uncertainty. So this one is 10 to the power of negative 0.2756 is equal to 2 over C best. Okay, and then the best C value. Wow, the same symbol that I use for y-intercept. Okay, this is C, not y-intercept, yeah? So C, the best, is equal to 2 divided by 10 to the power of negative 0.2756. Okay. 10 to the power of negative 0.2756. 2 divided by the answer. And I got 3.773 because I need to find the absolute uncertainty for C. Now, for worst y-intercept, okay, I put worst fit. This is the best fit. So the worst fit, I got 0.4489 equal to log 2 over C worst. C worst is equal to, I just keep the step, 2 over, right, 10 to the power of 0.4489. So I get a value, 10 to the power of 0.4489 and 2 divided by the answer, and I got 0.7114. 0.7114. Delta C would be, so I have plus minus 3, quite large actually, right? Because you know what? Because I didn't print it out, I do it digitally, so my values would not be that accurate. But here in this video, I'm just giving you the idea of doing it. Your values would definitely be different from my values. Look at the graph that I plotted. It might not be as accurate as the one that you plotted on the table, right? On your paper. So that is why my values will be quite inaccurate. So I'm giving you the idea of doing it. So C best would be 3 plus minus, oh, C best is 4. So, okay, plus minus 3, which is quite large for uncertainty. And then since there's no decimal point, I would round it off to 4 plus minus 3. So, which is quite large, seriously. Yeah, but if you do it on a piece on the paper that you have printed out, make sure that you print it on the full scale, full size, actual size. Instead of you shrink it, you will get the best answer ever, right? So E, the experiment is repeated, determine the length L of the rod that gives a value of T of 0.1 millisecond. Now this question, part E, usually you need to use back the equation that they suggested. So T is equal to 2L to the power of N divided by C. T is given a value which is 0.1, but millisecond, I would like to change it to second, right? Divided by 1000 or times 10 to the power negative 3 to length, right? Length to the power of, oh, I need to determine the length. And the N is just 1 here because they didn't ask me to include any absolute uncertainty. And I got 1 here over the C value, I got 4. So cross multiply, this one will be 0.4 times 10 to the power negative 3 is equal to 2L. L is equal to 0.4 times 10 to the power negative 3 divided by 2. So 0.2 times 10 to the power negative 3 meter. But here you need to put it in cm. cm. So if you want to put it in cm, you need to make sure that you shift this to the front so that you plus 1. cm is 10 to the power negative 2. So 0.02 cm. Okay, so the answer is 0.02 cm. This is just the overall idea on how you were supposed to do it. Like what I say, when you print it out, you plot it on a piece of paper, your value will be way, way, way accurate as compared to my value. So I hope that you could gain benefits from the whole paper that I discussed here, right? So if you face any problem or you need the full PDF answer for this paper, do comment below. If you face any problem, do comment below as well. You could reach me. at any time. Yeah. So thank you very much for watching. Right. See you again in my next video. Bye.